Dober dan. Mislim, da je prav, da povem po angleško. Welcome to this lecture today. We have two lectures. Actually, we have two speakers. One is here, one is here. Two famous researchers in their fields. And thank you very much for coming. We will definitely enjoy the two lectures, and I will give the word to Sasho to present the first speaker.
Dear colleagues, dear guests, it is my great pleasure to introduce the first speaker of today, Professor Bart De Moor. He comes from the University of Leuven, one of the oldest and the best universities. And he comes from the Faculty of Electrical Engineering, where he works in the area of control and systems engineering. But he has made quite a lot of contributions also more recently to the areas of artificial intelligence, machine learning, and their use, especially in healthcare. He has made contributions to science. He has made contributions actually to the transfer of scientific results to practice, being the co-founder of 8 spin-off companies. And most recently, he is very active in the area of scientific policy, being on the advisory or governing bodies of several countries, in fact, including Finland, for example. And just last week, they completed the Belgian, or rather the Flemish, national strategy for the area of artificial intelligence, which is my field of work, and this has been largely also thanks to Bart. So it is my great pleasure to hand over to Bart. Bart, thank you for coming.
Thank you very much. And thank you very much for welcoming me here in your nice institute. Actually, a couple of weeks ago, I was reading the biography of Ludwig Boltzmann, and it turned out that supervisor, the PhD supervisor of Boltzmann was Jožef Stefan. And of course, he is very famous for having discovered the radiation law, black body radiation, the T to the power 4. And that's also, if I understand, the symbol of the institute here. And Boltzmann, of course, understood that. But it's even more important for Max Planck, who basically asked himself this property of T to the power 4, what is the governing physical principle underlying this? And in order to prove the formula, he had to assume that energy is quantized. So that if you take energy, that they come in isolated packages, and then you can basically physically support the empirical law that Jožef Stefan discovered. And Planck did not believe his own result because he said, look, it's of course bullshit that you have to quantify energy. And he didn't know that basically he was the founder of quantum mechanics. So all of his life he was struggling with the idea that he was the founder of a discipline that he basically did not believe in. And that's of course the link here with your famous Jožef Stefan. When I talked to Sasha, before defining my topic, he said, look, it will be a very broad audience, so don't show any formula or don't start explaining the research you are doing at this moment. And that's why I decided to really cover a broad range of topics, so to also respond to the nice diversity in the audience here. And the title of my presentation is Life Goes Live, but I will go back a little bit in history also to make the parallel in a certain sense between the sciences on the one hand, sciences which is analyzing reality and trying to understand reality like Stefan Boltzmann and Max Planck did on the one hand, and on the other hand I'm an electrical engineer, and electrical engineers and engineers in general try to design reality. And so that will be a kind of duality in my talk. On the one hand, science, on the other hand, engineering. And another parallel I would like to make is a parallel between information technology. You can say that the 20th century was the century of information technology, and I will take you a little bit through the history of that. But if you ask me, and probably the next speaker will also speak about life and about cells and so on, the 21st century is a century of biology. And just like in the 19th century or in the 20th century, we had the first half of the century analyzing things, physics, quantum mechanics, leading to the transistor, and the rest is history. I think my opinion is that the same will happen in biology. We are trying still to understand biology, so that's the analysis phase. But at the end of my presentation, I will tell you a little bit about synthetic biology, which is basically designing life. And of course, that's very controversial. And so I hope that I create a lot of controversy in this presentation here. That's, after all, why we are scientists. So I will try to define a little bit what is science, what are models, but not go too deep in that. What is technology, what is engineering? And then when I was trained as an engineer, some of my professors said, look, engineering has to do with three spheres. It has to do with matter, it has to do with energy, and it has to do with information. And that was the status in engineering like 30 or 40 years ago. But in the meantime, we have added 4 more spheres, I think. And I will elaborate a bit on that. So there's a 4th sphere of sustainability, a 5th one of social interaction, a 6th one where the cultural dimension becomes very important. And I will conclude with the 7th one, which is the sphere of life, analyzing life, designing life. And then maybe the conclusion will be some utopic ideas. Can we or will we one day design living systems? And then we can leave the floor open for questions or discussions, or in the coffee break go under it. So what is science? I think basically the basic drive of any scientist is to understand the world, and in the recent history there were many attempts to do that. On the one hand, you can say religion is still there. That's one way of trying to digest reality in a certain sense. On the other hand, you have this tension between religion and science, and there are several evolutions in time. For instance, we all know what happened to Galilei, that he was not given the freedom of speech because of conflict with the church. And there's also this famous quote of Napoleon who addressed Laplace, and I saw downstairs here there is a first edition of one of the books of Laplace, and Laplace was one of the first scientists on the continent to introduce Newton's laws. And basically when he presented this to Napoleon, Napoleon asked him the question, where is God in your system? Où est Dieu dans votre système? And Laplace must have answered, God, I don't need that hypothesis. And that's basically very important. You can also go back to Descartes, where he say, I'm thinking, so I am, cogito ergo sum. And you have several phases. I'm only summarizing here the whole history of science in a couple of slides. To the right, you see the cover of one of the books of Francis Bacon, and he is considered to be the father of what is called the experimental method. And what you see on the cover of the books are the 2 pillars of Hercules, and they denote the world as we know it, and you see some ships sailing beyond those pillars of Hercules. So they are trying to find new worlds, they are trying to find new continents, and that's basically what science is trying to do, to find new things that did not exist or that we did not know before. Now, also in philosophy, there have been a lot of debates about trying to define science. And in particular, I like this type of approach by Karl Popper, who was, of course, a very famous philosopher coming from Austria nearby, but was also very active in England. And basically, he said a statement or theory is scientific when it clarifies and establishes its own weaknesses. And so contrary to what many people think, scientific theory is not true forever. It is scientific, but it has to identify its own weaknesses, meaning that if you find a counterexample, then the theory is no longer valid, and you will be invited, you will be instigated to find new theories to explain the phenomenon at hand. And so a scientific theory predicts many things, but on the other hand, it forbids more than it will allow. So that's basically a very nice criterion. They call it Popper's demarcation criterion, and in a couple of slides I will give you a nice example of that type of definition of science. And so this means that many theories, for instance, any religion cannot be scientific, because in a religion you never have the problem that something cannot be true. If something happens that you don't understand, you call it a miracle, or you call it the punishment of God. And that's basically an explanation of everything. So it's not a scientific theory. It does not forbid anything and so on. And also a lot of political systems like Marxism, liberalism, socialism, what have you, cannot be defined in this definition to be scientific. Another important principle is that if you have the choice between two explanations, that you have to take the simpler one. So if they have the same power of explanation, then you take the simpler one. And this is known as Occam's razor. Occam was a monk in England, and he said in Latin, "Entia non sunt multiplicanda, praeter necessitatem." And that's basically saying that choose the simpler explanation. Another thing we have to be careful in science, if we have scientific theories, if we have models, then I always refer to this painting of the Belgian painter Magritte, who said, "Ceci n'est pas une pipe," this is not a pipe. So it's only a picture of a pipe, meaning that you cannot smoke with it. So basically, if you have a model, models should not be confused with reality, and that's a mistake that many students, many engineers make. They have a model, and they think that the model is the truth, and that is reality, and basically reality is not just another model. It might be completely different in certain ranges of operations from the model you are studying. And we call this in engineering the "ceci n'est pas une pipe" effect. When you're working with models, when you're working with scientific theories, you have to be a bit careful. Technology has many definitions, but one that I like is that technology, basically, as we look at the evolution of the human race, that technology is a transbiological evolution on top of the natural biological evolution. So basically, by using technology, by invoking technology, we are speeding up the natural evolution. And that's, of course, a very important point of view, because it means that typically we're just speeding up evolution, and that we are trying to control how the humankind is evolving in the universe in a certain sense. And technology is just like a kind of prolongation of our abilities as a human being to influence or to interact with nature. And what is an engineering? Engineering, I like a lot of definitions of engineering, but I think one of the central words in any definition of engineering is that it is design. It's about designing things, it's about designing solutions, about designing software algorithms to solve certain challenges and problems. So I think the word design is really important when we talk about engineering. Okay, now what are these 7 spheres? Let me elaborate a little bit on these engineering spheres. So matter, and here I will use Newton's laws and also illustrate the proper scientific demarcation criterion to define what is scientific. So basically you have several pictures there of Kepler, of Newton and Einstein, and Kepler was the first one to define Kepler's law. There are basically 3 laws. I'm not going to elaborate on them, but the first law is basically saying that if you have a planet and if you have one sun, then the sun is basically in the focus, what is called the focus, not of a circle, but of an ellipse, and basically an ellipse has 2 foci, and this, the Earth, the planet, is moving in an ellipse around this sun, which is in the focus. And basically, if you then go to Newton, what Newton did is he took these laws of Kepler as a kind of experimental evidence, so it was basically validated by measurements, and then he formulated 2 very important laws. And I think one of the biggest scientists, largest scientists reputation-wise in science is for sure Newton. Because in order to do that, he had to invent differential equations. So you know Newton's first law is F, the force, is equal to the mass times the acceleration. And the acceleration is the second derivative of position. So that's basically a differential equation. And so he invented analysis, he invented differential equations and the inverse operation integrals in order to write down this law. And then he also provided an explanation for the force, in which he said that basically if you have two bodies with a small mass m and a large mass capital M, then the force between them is proportional to the product of the masses divided by the distance between the two. And if you connect these two laws, basically if you do all your calculations, then you will find that the Earth moves in an ellipse around the Sun. It's a consequence of these equations. So in a certain sense, Newton went in an inductive way from Kepler's laws to these two laws, for which he had to invent a lot of mathematics. And this is basically one of the first occasions in the history of science where mathematics has become very prominent as it is today. Mathematics was one of the underlying cornerstones of all of science. And then, you know, there was a problem, because I told you that theory is scientific if it if it describes its own weaknesses. So what is the weakness of Newton's worldview in this case, his equations? If I give you a planet who does not move on an ellipse around the Sun, then there is a problem, because you cannot explain this with Newton laws. And there is a planet, basically the planet Mercury. It moves like an ellipse on the Sun, but the ellipse is tilting slowly in the third dimension. They call it a rosette, so it's a kind of geometrical figure which does not follow from Newton's laws. And it took the genius of Einstein to really explain what's happening here. Basically, one of the secrets is that Newton tacitly assumed that the two small m's in the two formulas are the same. So the m in the first Newton law, F is m times a, and the m in the gravitation law are the same. And exactly Einstein said, wait a minute, this is a hypothesis, and you have to kind of start from that hypothesis. And then by logical thinking, by using a lot of mathematics, he discovered basically the general theory of relativity, which is till this day very valid. But it's a kind of more sophisticated version of the gravitational theory of Newton. Now, this does not mean that the theory of Newton is not scientific. It's a scientific theory because it could identify its own weaknesses. And up to this day in engineering, we often use Newton's law because it's a very good first-order approximation of the more general theory delivered by Einstein. And so this is a nice example that says many things. It shows you when a theory is scientific. It also tells you when it can be invalidated, and it also tells you that mathematics is increasingly important from that moment on in science. And actually there was a Nobel Prize winner in physics, Eugene Wigner, who wrote a paper, and I can really suggest you to read it. It's a very nice read. It's not very complicated. You can download it from the internet, and it's called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And I could elaborate on this for several hours, why it's such a miracle that mathematics is so productive in science and engineering, but nevertheless he was one of the first persons to state that kind of wonder why mathematics is really so effective in physics, in engineering, and in many other things. Another thing you can look at is the evolution of society as the science evolves. And of course, when we think about matter, and also about energy, so to say, then if you look at the 18th century, the 19th century, that was of course the invention of the steam engine, so that's the engineering, the mechanization of the textiles industry, which already started in the Middle Ages, and of course you get all kinds of networks, so you get railroads, you get roads for transportation and so on, and also as an energy source you see that people started using water and coal. And that also induced some social innovations, because we evolved from what you could call a rural society towards an industrial society. And of course, if you talk to sociologists, then there's a big debate whether the industrializations or new technologies that induce social cultural evolutions, or that it's exactly the other way around. I mean, there's a causality dispute here, but basically you can also say that at the same time you see also drastic changes in society, and that's also what we see today, of course, with information technology. Now, if you go to our second sphere, energy, You can debate whether the periodic table of Mendeleev is energy or matter, but it doesn't matter because we have E is mc squared of Einstein, so they are basically the same. But then you have a breakthrough in the 19th century, which is Maxwell's laws. Actually, the way that you see it written here were not the equations that were derived by Maxwell. Maxwell had something like 20 equations to explain electromagnetism, but the equations were cleaned up by a famous engineer called Heaviside, and he basically he summarized Maxwell 20 equations to the 4 equations as we know it today. I'm not going to elaborate on the meaning. It describes the relation between electrical fields and magnetic fields and the speed of light and so on and so forth. But basically it's again a manifestation of the fact that mathematics can really explain very accurately the electromagnetic reality in this case. Now, if we go back again to society, we see we have a second industrial revolution in the 19th century. So we start doing mass production and consumption. We get new energy sources, electricity and oil. It's also the beginning, of course, because of the oil, of the chemical industry that starts developing. And of course, you get these sociological consequences or interactions with new political economical theories like Marxism, liberalism, Adam Smith, the invisible hand, and so on and so forth. And for the first time, also governments start playing a role as a regulator and as a facilitator, not always in a nice way in the 19th century, but nevertheless, it's the first time governments also start getting involved really drastically in society and in engineering. Then is a very interesting period in the 20th century, where, as I told you, you have a whole period like 50 years of what I could call analysis or science. So it's basically start with Maxwell's laws. I alluded to the quanta of Max Planck, and you have the whole history of quantum mechanics here. And then you have all these famous people that are depicted here, also the information theory of Shannon, which is a kind of mathematization of information. And then in 1950, some miracle happens because there are 3 engineers of Bell Labs in America that invent the transistor. And the transistor, of course, is an essential elementary building block of the information society as we know it today. Of course, all the people mentioned here got a Nobel Prize, including those 3 engineers. You see here the first transistor to the left. It was a kind of macro device. And now these days we make chips which contain billions of transistors on 1 square millimeter of silicium. And maybe you've heard about Moore's law. Moore is still alive, Gordon Moore. He is the founder of Intel, the big chip producing company. And back in the 60s, he formulated a very famous law. It's a kind of empirical observation that the computational power of our computers is doubling every 18 months. And this is an exponential law. So in order to give you an idea of what it means, you have to think of your bank account. When you would have a bank account where you put 100 euro on your bank and it would double every 18 months, it's a very good interest rate. The interest rate would correspond to 56%. I always tell my students, if you have a bank like that, don't tell anybody, because if everybody will jump on that bank, and of course the interest rates will go down and so on and so forth. But today you would give your life for an interest rate of 5%, typically it's 0% these days, but 56%, that's exactly the interest rate, the exponential doubling every 18 months of our computational power. And this means that our computers are becoming more and more powerful. So basically, you could say that computing is not the bottleneck anymore. And even if there would come an end to Moore's law, we are now already investigating quantum computers, so based on completely different principles induced by quantum mechanics to build quantum computers that will even be faster, even be more powerful, and so on and so forth. So in all applications, and I'm going to show you some of them, you can safely assume that computational power and memory is basically there, so that we are not building against walls there, so that we are not hitting any walls there. big thing of the second half of the previous century is the design of a chip, because you might think that is easy, it's very complicated, but the idea is that engineers, that they work in a modular way. It's just like building your house, where ultimately you have to build it using bricks, but when you define what you want to have in your house, you don't think in terms of bricks, you think in terms of the rooms, a living room, a kitchen, a bedroom, a garage, and so on and so forth. You think about utilities, and then you make a plan, and ultimately that will be built by bricklayers, and they will using bricks. Well, a chip is designed in exactly the same way. If you want to design a system, an iPhone, and an iPhone includes a lot of electronics, then you think about the functionalities. It's just like the rooms in your house. So your iPhone will need memory, you will need clocks, you will need control, you will need computation time, you will need communication interfaces, and so on and so forth. And you need utilities, and once in a while you need power. And ultimately it's a plan, so you have to imagine that a chip, an iPhone, is built by thousands of people. They all work in a modular way, and they follow a certain plan. So it's really a big, massive business plan if you want to make a new thing. And of course, fundamental research here means that you have separate teams that will design new memories. I mean, they use new technology, new breakthroughs to design better memories, and so on and so forth. But once you design a system, you think in this modular way, and I will come back to that later on when we talk about biological systems, because the idea of building biological systems from scratch, synthetic biology, is also essential when you think about modules. So modular ways of thinking in terms of building blocks will also pop up in biological systems. And of course, a consequence of the information breakthroughs the last 50 years is that today we are confronted with a tsunami of data. And sometimes we call that the fourth paradigm. The first was empirical based let's say in the Middle Ages. From Newton on, you got like theoretical models, Newton's laws, for instance. That was followed by computations. We have computers since 50, 60 years. And the fourth one today is what you could call data-driven, that we do not do the following like we used to do classically. I have a hypothesis, and then I'm going to look for data to check it. Today, it's the other way around. I have a lot of data. What are the hypotheses that I could check? So that's what's called the fourth paradigm in data science. Now, we consume a lot of data, and I'm not going to elaborate on these numbers here. You can quickly look for yourself, and I will also make available my slides to put on your website or to distribute it. But basically, when we now start training engineering students, this is like lecture 1 in engineering is trying to grasp the orders of magnitude, so that when we say a terabyte, that you basically know, you realize what a terabyte on information is. That's a lot of data. And I will give you some numbers, 20 minutes still, yeah, so that's fine. I will give you some numbers. Now, to convince you of the fact that data are pervasive in our society, I just gave you a couple of slides here in the subsequent part of the lectures of projects that we have been doing the last couple of years in Belgium and in Europe. And to give you, I will not go into technical details and how we derived these models and what type of machine learning things we did and system identification and so on and so forth. But the emphasis will be on the data. And so if you look at something like a smart grid, you see here the map of Belgium, and you see also the density of grid lines. So these are electrical lines between several posts. In Belgium, you have about 3,000 transformer posts. So you see a picture there of one of them. And every 15 minutes, the power consumption of these transformer posts is measured. And they do that since 5 or 10 years. And so the data set we get is depicted to the right bottom. So you see there the days of the week, and you see also the week. So this is the data of 1 year. And basically you see there are lots of seasonalities. In the picture to the right, you see the typical days of a week. So Monday, Tuesday, Wednesday, Thursday, Friday in one post have the same type of behavior. The weekend is different. And to the other plot here, you see the difference in seasons. So you see that the power consumption in the winter is different from the power consumption in the summer. And basically, this is the data set you get. This is only for 1 year, but you get this for 5 years. And then they want to use it in several ways. So can we use it in a simulation? So can we understand the dynamics of what's going on there? Can we identify the type of customers that is consuming power per transformer post we have? And can we predict, and can we also use this in maintenance? So when we know, for instance, that one of the nuclear power plants in Belgium is going down for maintenance, can we simulate that the demand of the consumers can still be satisfied? And of course, the answer is yes. I mean, we can use all kinds of AI-driven techniques. So basically what you see here is a prediction, so we can very accurately predict the power consumption. One of the inputs here is the weather prediction, so we can look 1 week or 2 weeks in advance using, we take in weather predictions, temperature predictions, rain predictions, and so on and so forth. And these are used as a priori information in the simulations that you see here. And we can also cluster the customers. So you see here 6 typical clusters. They can be households that are behind such a transformer post. They can be large industries, and so on and so forth. So you learn a lot from these data, provided, of course, that you have these sensors and that you have all these measurements. Here's a completely different application area. We had a contract, or we have a contract with the Belgian national soccer team, and you know that they are doing very well, and we are very proud of that. And I don't know whether it's because of the software we have. You wish, of course. But basically, what are the data here? Well, players move in 2 dimensions over a field, so we have like 10 cameras all over the field, and from image processing we calculate the coordinate of each player. 22 players, 3 referees, also we measure them, and the ball is measured in 3 dimensions because the ball, of course, moves in 3 dimensions. Actually, the ball is, in image processing terms, recovering the 3 coordinates once a second of the ball is a big challenge because, you know, when the ball comes in front of an advertisement panel, you lose it. Mentally, we still see it, but the camera does not see it. So you have to predict, you have to use Kalman filters, and so on and so forth. But ultimately, what is the database here? It's for 90 minutes of soccer. Every second, we have the position of every player and and the ball. And then, of course, people say, now you can detect offside. Yeah, but we don't do that because that's the referee. And the bars afterwards still have to do some business. So whether something was a penalty or offside, I mean, we don't interfere. But what we do is complete tactical analysis. If the assignment of a certain player was to cover another player or to cover another zone, or the physical performance of every player, we can deduce from these numbers. So we can also apply all kinds of nice things. For instance, here you see what is called the player polygon. And suppose that the red players are attacking in that direction, and the blue ones, these are the Italian ones, are the defenders. These are the Red Devils against Italy. And if the Red Devils attack too enthusiastically, if they don't score, then, of course, the Italians will have a counterattack. If they play the Catenaccio, they will have a counterattack. And if the Belgians are not back fast enough, then the Italians will score. So how do you quantify that mathematically? Well, we have the coordinates of all these players. We calculate the center of gravity of this player polygon, and if the center of gravity of the red players comes in front of the center of gravity of the blue players, you get a kind of label. The computer algorithm will detect that and will say that was a dangerous attack. And later on, you can, using video images, you can select those dangerous phases, and then you can study with the players what went wrong. And that's one of the applications, and there are a zillion of them. You see here the coverage of one player, and so on and so forth. So it's a very fun project to discuss about soccer in a mathematical way. Some of the trainers don't get it, but you have a couple of intellectual trainers that really understand what we are doing. The next sphere is sustainability. I don't have to explain this to you. Basically, that can be summarized that we do not inherit the world from our ancestors, but we have borrowed it from our children. That's not a new statement. It was the famous French writer Antoine de Saint-Exupéry, you know, the Le Petit Prince, who said that. And that's increasingly an important type of challenge for the current day world. Here you see the type of measurements that we use in order to do sustainability. So we can talk about tornadoes, we can talk about satellites, you can talk about energy consumption. You see there the lights in Europe overnight. So you clearly see London and Brussels and Paris and Rome and so on and so forth. And actually the picture to the left shows you all the satellites and the International Space Station. So there are thousands of devices out there in space that allow us to look at the Earth. And also, of course, don't forget the GPS systems that give us the coordinates. And one example of a sustainability project, smart cities if you want, is modeling of the ozone concentration and the fine particle distribution over Flanders, so the north part of Belgium, in which we have assimilation stations, so measurement stations, and in which we have also validation stations. Validation means that we don't measure there, we don't use those measurements to model the thing, but we use the measurements in those stations to see whether our predictions work sufficiently well. And it turns out that using these advanced mathematical techniques, machine learning, but also many techniques of systems theory, that we manage to describe very accurately. So the resolution is here about 100 square meter. So in a square of 100 square meter, we can accurately predict the concentration of fine particles and of ozone. And that's one of the other examples where we use a lot of data, including three-dimensional data. A type of similar project is in many areas. This is one in close to Leuven. You have flood prevention systems, and these days we equip such rivers and all the side rivers. You see the whole river system depicted there. We equip them with sensors. And so you have hundreds of sensors, maybe thousands of sensors all over the rivers that measure the flows and that measure the levels and so on and so forth. We have the weather prediction upstream, so we know when rain is going to fall. And then we simulate the whole system, so not only one river, but the whole river system. And then when there is a danger for flooding, we can control the whole thing. We can even open up dikes so that not cities are flooded, but that prairies are flooded and so on and so forth. And so that's a fully automated system. Of course, you always have a human in the loop, but that's a fully automated system where we use things like model predictive control, a lot of mathematical models, weather predictions, and so on and so forth. And this is running in real time. So every 10 minutes, we get an update of the whole situation in the control room. Another type of data in sustainability is traffic. We have thousands of cameras on the roads. We have thousands of loops in the roads. And then you can do things like incident management, like speed harmonization, ramp metering. These are all these days systems that are really completely automated and that use a lot of data every day, and that can also be modified according to the weather conditions. So basically, this is an example in sustainability. I'm not going to elaborate on all the details here, but these are things we have been doing. Social is, of course, another new sphere. Because we are connected. And here you see another logarithmic picture that depicts the kilobytes per second that we are sending through our fibers and to our connections per second as a function of the years. This is a semi-logarithmic plot, so you have a linear scale on the x-axis and a logarithmic scale on the y-axis. So this is also another manifestation of the exponential evolution of the connectivity in the world. And of course, this is also a nice animated GIF file where the red is intensive internet traffic and the blue is less intensive internet traffic. And basically what you see here is the day-night cycle over the Earth, that when now it's America that's active, now Asia becomes active, Russia, and now Europe and Slovenia become active, and so on and so forth. So that's basically a visualization of the interaction that is induced, and I'm not going to elaborate on social media here, and so on and so forth. Culture. Why do I have a picture of Steve Jobs here? Because Steve Jobs is, of course, known for inventing the iPhone, but what I liked in particular is that he said that design is important. When you make a new technological system, it should look nice. I mean, this is a cultural dimension that is brought in a technological device. Why do you want to have an iPhone? It's not better or worse than another iPhone, than another GSM, another mobile phone, but it's nice. I mean, it's nicely designed and so on and so forth. And I think the big contribution of Steve Jobs was not really technologically, but was bringing in this cultural dimension in technological devices. And by the way, Apple will be confronted with more and more difficulties to be more and more innovative in this respect. Technology that will follow automatically, but what is the next new nice thing that you would like to have that they will invent? And actually they don't know. I mean, there's a kind of crisis in Apple now because of this dimension. They suffer in their cultural dimension. One of the nice projects that I also did is in the secret archives of the Vatican, and you might imagine what has information technology to do with cultural heritage. Well, we digitize old manuscripts. These are manuscripts from the 14th and the 15th century. You see here one of our researchers who is working in the secret archive, so it's very labor-intensive work, where we digitize those manuscripts at 1 million or 100 million pixels per image. And then we use those images to put them on our website so you can consult them publicly. But we also do data mining on that. So for instance, we have thousands of manuscripts. About 1/3 the composer is known, and about 2/3 the composer is unknown, it's anonymous. But we analyze the musical structures in those manuscripts. It's polyphonic music, so you have several voices. And then you can deduce features, as we call them, musical features. And then you can try to identify anonymous manuscripts and see which composer could have. So that's an example where we generate a hypothesis from data. So we don't start from the hypothesis, no, we start from the data, and we generate the hypothesis from the data. And that turned out to be hugely successful, so we even discovered sometimes new manuscripts, new songs that were unknown from known composer, and so on and so forth. Another thing that our computer algorithms can do, you see the notation in polyphonic is still Gregorian, and many people that are musically trained don't read Gregorian, so we have computer algorithms that translate Gregorian music notation to modern music notation. It turns out to be very difficult because Gregorian notation is very good in the pitch, in the frequency, but the rhythm is kind of open for interpretation. When you see a long note, nobody can tell you how long that note should be. It just means long. And when you see a black note, it's short. But nobody knows what long and short means. And that's one of the challenges we do. So we can even computer-wise interpret and make specialist experts listen to that. And then they will say, no, no, this doesn't sound right. I mean, it must be different. And that's another way of generating hypotheses. And this brings me in the last part of my presentation. It's about life. Again, we have there a whole scientific era of discovery, which is basically this impressive list. And you see Mendel, you see Crick and Watson there, you see the two famous editions of Nature and Science, where the human genome was published around 2000. You see Bill Clinton there with the two leaders of the two concerns that did it. One was a private concern, the other one was a publicly funded concern. And so basically that's a very important accomplishment, that since 20 years or so we have the complete human genome. And even more, we can sequence every individual genome, whether it be from a healthy person or for a tumor or from an animal. We can really sequence the whole thing. So that's one of the big truths. And that's the moment also when we started being active in a lot of health-inspired applications, because when these days you go to a hospital, then you have a tsunami of data. So you see here several devices. You see magnetic resonance, you see mass spectrometry imaging. To give you just an example there of mass spectrometry imaging, that's an invasive technique where you take a slice, for instance, of brains, for instance, of a rat. And that's a two-dimensional picture. And in the third dimension, per pixel, you measure the concentration of molecules, and that's the spectrum you see there. You measure the concentration of molecules in the third dimension. And this is a vector of about 250,000 numbers. So suppose you have an image of 1,000 by 1,000 pixels. You have 250,000 numbers in the third dimension. You can calculate for yourself how many data that is. And that is for one slice. If you slice the whole brain, you have a three-dimensional picture with, for every voxel, as they call it then, the molecule distribution. So that's a four-dimensional object. And when this evolves as a function of time, suppose we could do this in a non-invasive way, and we're treating a tumor, then you have a five-dimensional object. So three spatial dimensions, one frequency dimension, molecules, and one time dimension. And then the question is, how do you model such an object as a function of time? How do you model a four-dimensional object that evolves as a function of time? And that's our current day research, that we are trying to recover the mathematics to do exactly that. Another example you see here, it's a microchip, as it's called. It's a DNA chip, where basically you can take a sample, a blood sample, for instance, of a tumor, and basically you confront here the gene activations in a tumor with the gene activation levels in healthy tissue. And the difference in color tell you which genes are reacting differently in the tumor as compared to the healthy tissue. And that's one sample that gives you about 25,000 numbers. They are about, well, a little bit less, about 20,000 genes in humans that are there and that you can measure. And also here you have an exponential evolution. The Human Genome Project was billions, 300 million of dollar effort. 10 years ago, 12 years ago, Watson sequenced his own DNA. That was at $1 million and was done in 2 months. These days, we are getting close to the fact that sequencing your own DNA is a matter of hours, and it will cost about $1,000. So it will be a kind of routine thing, and it's also another manifestation of the exponential evolution in technology. And of course, medical applications are source of large numbers. You see some here. Let me pick out one. If we would decide to sequence all newborn babies in Belgium, there are about 125,000 babies born in Belgium, that would give you 125 petabytes of data per year. That's a lot of data. I can assure you that's a lot of data. If you sequence your own genome, and if you don't do it redundantly, but to be sure you should do it redundantly, but minimally you need 750 megabytes. That's one CD-ROM. So on my iPhone or on my iPod, I can carry about 1,000 or 1,500 complete human genome sequences on that device. So 750 megabytes seems a lot. It's one CD-ROM on which you can store, in principle, one human genome. And of course, there have been papers now saying that just like mathematics was unreasonably effective in physics, it's now turning out to be unreasonably effective in biology. And doctors hate this paper, because I always tell them you have become medical doctor because you didn't have to do anything with mathematics. I mean, they became medical doctor by elimination, so to say. And they hate that, because these days they are confronted with a lot of mathematics. They have these data. We try to explain them what artificial intelligence is, what mathematics is, what machine learning is. And they do their best, but deep down there, they hate it. And that's basically a nice source of research for engineers. So the complementarity is very big. So Dr. Algorithm is coming. It goes without saying. And typically, we call it decision support systems. The support is to have compassion with the medical doctors. Because if you say, we are going to make a decision with an algorithm in your place, of course, it's denying the medical responsibility. It's ultimately the doctor that is still responsible for what's happening. It's like the automated pilot in an airplane. In principle, it can fly the airplane, it can lift off, it can fly, it can land completely automatically. But of course, it's still the responsibility of the pilot. Why? When something goes wrong, then he will take over. And it's the same with making diagnostics and diagnosis that can go wrong, of course, and then you still need a medical validation. What you see here, just one example, it's based on DNA chips, and we here cluster or classify 3 different types of leukemia, and the columns of this matrix that you see visualized here are patients, the rows are genes, and basically you see that you can recognize, you can classify a certain type of leukemia by looking at which genes are active in that type of leukemia. And here it's an obvious example, it's an easy classification where you clearly see the fingerprint of ALL, the fingerprint of MLL, and the fingerprint of AML. Now this can be used as a diagnostic device, because if you have done this for a couple of thousands of patients, then when a new patient comes in and you think there is a kind of a leukemia, you just take a blood sample, put it on a DNA chip, and then you look at the pattern and you try to classify the pattern of that patient by correlation analysis to the patterns that you see here. And that's a first indication of the type of pathology that this patient might suffer from. Another example is where you're trying to look for candidate genes in a certain disease, and then you have sources from DNA chips, you have sources from proteomics, you have a phylogenetic tree, so you're looking at the relationship with other animals in evolution and so on and so forth. And the question then is, which 5 genes are most important for this type of pathology? And then we use machine learning and all kinds of advanced statistics to come up with a kind of consensus ranking. So it's basically a search engine, if you want, where at the end you have a ranking that tells you these genes are the most relevant depending on these sources that you have given us here. And we call that data fusion. So you use several databases to come with a consensus prioritization. And then the researchers can concentrate on those 5 genes to start with. But these are only a couple of examples, basically where we will go to an era where you have more and more devices, as you see here. I think the most spectacular one here is the neuron on a chip. So there are experiments going on in Leuven where we grow living human neurons on a chip, and they interact with each other, so they communicate with each other. I don't know what they are thinking, but basically they communicate already. And maybe to tell you a couple of things about synthetic biology. Oops, I was too fast here. You see here, if the movie works, yeah. You see here a fascinating picture. It's not new, it's a movie. It's more than 50 years old, and it's a neutrophil that is chasing a bacteria among red blood cells. So it's in a kind of disc, it's in a lab. But you see that this thing, this blob, is chasing the whole thing. And so then I ask my students, does this neutrophil have brains? And of course the answer is no, it cannot have brains. So how does it know where to move? Let me see it once again. How does it know where to move? How does it feel the bacteria? So it's a process called chemotaxis. It kind of smells small traces, small molecules that are left behind by the bacteria, and it has an actuator system, so it can move in this liquid and ultimately swallow the bacteria. And so the question is, of course, is this intelligence or not? No, it's just a control. It's a stupid system. But the idea is that for engineers, can we reproduce this? So can we manipulate bacteria so that we get new bacteria that have a functionality that does not exist in nature yet? Of synthetic biology, you see these are the modules. You have inputs, outputs, you have clocks in there, you have memories, and so on. These are all biological things. So you have now websites. There's a famous competition called iGEM, Synthetic Biology, a website in MIT. And there you can download all kinds of DNA information. Suppose you want the DNA sequence for a clock. You can download it. There are maybe like 10 clocks on there. You can download, you need a clock for once a day, you need a clock once a minute, and so on. So you can download the modules, the DNA module that you need to do that. You can download a module that will kill the cell. You can reset the cell. And the example that is given here, so this is the modular approach. and you see you get very complicated architecture. So it's very reminiscent of chip design that we are now doing in biology. And this is one of the results you get. So the bacteria here was built in such a way that it can kill cancer cells before you see the cancer cells on any scanner you can imagine. So we are talking here about individual cancer cells. And the idea is that you swallow the bacteria, you drink it, and then it starts sniffing around in your body. And when it meets a cancer cell, it detects whether it's cancerous or whether it's not. And when it is, it will produce a local medicine in order to kill the cancer cell. And here you see some simulations where you have a certain memory. You see that here there's cancer in a cancer cell. It will release the medicine. After a while, the cancer cell is dead. It detects a new cancer cell. It releases the medicine again. And then after a while, it doesn't find, for instance, after a week, it does not find any more cancer cells. And of course, you don't want that bacteria to wander around forever in your body. So the timer goes on, and after a week, it will kill itself, and it will basically leave your body in the natural way. And so this is not science fiction. It's basically something that is happening now. And this brings me to my last slide. Suppose we can design life, and of course we are only in the beginning of this phase where we can modify life, where we can design bacteria with all kinds of functionalities for energy, clean tech, human therapy, artificial organs, and so forth. And don't say it's impossible, because if you would go back 60 years to the beginning of the transistor, then you could also not predict the internet and all the things we do today with intelligent systems, but they are engineering systems. So imagine that we look ahead for 50 or 60 years, what could be possible? And I think technologically all these things will be possible, but of course we are now modifying life, we are designing life, so you will have three basic deficits that are really important. Will we allow it? I mean, that's a legal aspect. Democratic, I don't mean that we will forbid it, but now many things are forbidden by parliaments because our politicians do basically not understand the science behind it. And that makes them afraid, so they call it Frankenstein food, for instance, everything that is genetically modified. And that's not a scientific attitude. So basically, we also have an objective of science sharing, of patiently explaining what we are doing to the decision makers, the political decision makers. And of course, we have ethical problems. Ethics, for me, basically means that you can suppose that technologically anything can be built. If tomorrow you will make a mouse that is blue, that can change color when it sees a human, and that has 5 feet, we can do it. I mean, suppose you can do that. Then the question is not how you will make that mouse, but whether you will make it or not. So the more technological possibilities you have, the more choices you have to make. And that's the very definition of ethics. What will you choose and why? And what will you forbid and why? And so is this utopia? I don't think so. We have a lot of problems, not only technological, but also societal, we have to deal with. But basically, I hope you got the message. There is a phase of analysis, a phase of design, and there's a big parallel between information technology and biology in the near future. Thank you very much.